Okay, now we'll see how to determine the electric field when we have arbitrary charge distribution. So in the previous case, we assumed that we have symmetry, and when we have symmetrical distribution, then we can apply Gauss law to determine the electric field given the charge distribution. But if we don't have symmetry, then we can't use Gauss law. And in those cases, we need to have a different approach to use or to determine the electric field. So from physics 2, if you remember, if we have a point charge, let's say if we have a point charge, then if we want to determine electric field at the distance r from this charge, let's say this charge is q, then the electric field at this point can be determined using q over 4 pi epsilon naught r squared. So if we have a point charge, then we can determine the electric field using this expression. Now we will just modify this. Now assume that we have arbitrary charge distribution in this surface or in this volume. Then for a very differential charge, let's say we have dq here. So a very small differential charge dq. Well, we can assume that that's close to a point charge. Then the differential electric field at this point, the differential electric point or the partial electric field that can be generated due to this point charge or this differential charge can be expressed as dE. So we can say that dE, the differential charge due to this, the differential electric field due to this charge is nothing but dq over 4 pi E naught times r squared. So if I say this is r, so this is how we determine the electric field. Now our goal is to determine the total electric field at this point. Let's say this is point P. At point P, due to the entire volume or surface or line distribution of charges. So our goal is to determine, let's say this is, we have QT. So our goal is to determine the total E at point P due to this volume or surface distribution of charges. Now this R is the distance between this dq and dE, the differential distance. So therefore we have to find dq, sorry, we have to find qt. So qt is nothing but, if it is volume, then it's the volume integral of dq. If it is surface charge distribution, then it's going to be over the surface. If it is line, it's going to be line distribution of charges. So I will introduce this very simplified expression that helps us to determine the total electric field at let's say this is point P. At point P, due to the volume or surface or line distribution of charges. So if you see this expression, the first part is, this is rho v dv, which is the volume distribution of charges. So it's total volume, so it's total charge, and divided by r squared, where r is the magnitude between this point and that point, right? So this r is the magnitude of the distance between the point charge and the field point. So for our case, this source point, so this dq, so this point is defined as a source point, and the point at which we determine the electric field is our field point. So we use prime to show that that is a source point, right? Because both the source and the field point are in this XYZ plane. So if I use the same XYZ, then I might confuse this term. So to avoid that confusion, let's put a prime for source point, and if you see x prime, it's that coordinate shows or tells us that that is where we have the charge distribution. And if we don't have any prime, and then that shows that that is the point where we want to determine the electric field. So that's what you see here. So we have a prime, x prime, y prime, and z prime, and the same is true here. That shows that this is to determine the q or the charge distribution, and r is the distance, the magnitude of the distance, the magnitude of the vector between the source point and the field point. So if we have a volume charge distribution, we have dV. If we have a surface charge distribution, we have ds. If we have line charge distribution, we have rho L. And the other thing is, if you see here, this is AR. So that always goes along the direction of the line between the point charge and between the source point and the field point. If you see, due to this dq, the electric field line will be along this direction. Now, if you see, it's not along x, it's not along the y, or it's not along the z. So this is the unit vector. It's along the unit vector between the source point and the field point. So this, we say this is along AR, where R is the vector between the source point and the field point. So it's a unit vector. So AR is basically the vector R between the source point and the field point, and the magnitude of R. If you divide this, we'll get the unit vector. So that's why here we have a unit vector AR, and that is replaced by R divided by magnitude of R. So that's why you see R cubed in the denominator and R in the numerator. So R over R, the magnitude of R will give us the unit vector, and that is, so that shows the direction of the electric field. So always the electric field points along that unit vector. So in all the equations, if you see, we have R cubed. That's because we replaced the unit vector with R over R squared. But if I use the unit vector instead of this is also similar to 1 over 4 pi E naught integral of rho s ds prime over R squared, where R is a magnitude, and this multiplied with AR. And if you write for the line charge distribution, this is again the same as 4 pi E naught rho L dl prime over R squared times AR, where this AR is the unit vector between the source point and the field point. So always we have to specify the source point, or the x, y, z prime, and then we have to specify the field point. We have to determine the vector between the source point and the field point, and then we substitute the values and integrate. And how do we determine R? R is the vector between the source point and the field point. So it's very easy. So this is the origin where we have 0, 0, 0. So the vector between the origin and the source point is R prime. The vector between the source point and the field point is R. Then this is R prime plus R is equal to uppercase R, right? So this was just, we're using a vector addition. So this vector plus this vector will technically give us this vector. So R prime plus R equals to R. From here, we can determine the vector between the source point and the field point. That is R minus R prime. So from this, we can determine the vector between the source and the field point. Then if I know that, then I will just substitute that here in this equation, on one of the three equations, and then solve for the electric field. So always, if we have arbitrary charge distribution, or if we don't have any symmetry, we'll use this expression. And this is based on this equation. So we assume that we have a point charge, and for that point charge, the electric field can be determined using this expression. So if I have dq, then for that dq, I can determine dE. And to determine the total E, or the total electric field due to this charge distribution, then I have to integrate both sides based on whether I have volume charge distribution, surface charge distribution, or line charge distribution. Okay, let's see this example. So in this example, we're asked to determine the electric field along the z-axis. So generally, the field point can be expressed like this, where this is this is a distance rho from the center, but in this case, rho is 0. So this is 0. So that means the field point is also on the z-axis. Let's say this is the field point. So this field point is 0, 0, z. So we want to determine the electric field at any point along the z-axis. So we're given a line charge density, and that is also along the z-axis between z1 and z2. So the first thing we need to do is we have to determine r, where r is the vector between the origin to the field point, and r prime is a vector between the origin and the source point. Let's say the origin is here, so this is 0, 0, 0. So let's say this is the origin. So r is the distance between this. It goes from here all the way up to here. So this is r. So this is r. The vector from the origin to the field point, where the field point is here. Now r prime, let me use a different color. R prime is the vector, again, between the origin and the source point. So the source point z prime is somewhere here. So again, from here, from the origin to the source point, we have r prime. We have r prime. So the vector r is between these two. So vector r is, the uppercase r is r minus r prime. But in this case, r is, it's obvious, this is at the distance z from the origin, and it's pointing along the z-axis. And r prime is also again along the z-axis. It is z prime, but it's pointing, again, it is also pointing along the z-axis. So from here, r is z minus z prime, and it's pointing along the z. Now the magnitude of this vector, is square root of z minus z prime square, and plus, we don't have any other components, plus 0. The other components are 0, and since we don't have any other component, this is nothing but z minus z prime. So the magnitude is z minus z prime, and the vector is z minus z prime pointing along the az axis. So we have these two things. So the denominator, if you see, what you see here is a magnitude, and the numerator is a vector. So we have r, we know the charge distribution, it is given here, and we know dl prime. dl prime is a differential length for the charge distribution, so it is along the z-axis. So this is, if I say this is a differential length dl, and it's along the z-axis, so I'll use, this is dz prime. We use prime for the source points. So dl prime is dz prime because it is along the z-axis. So what else do we have what? I think we have all the things. What we need is just simply plug the values. So now let's just substitute these values and solve for E. So E is electric field vector for the arbitrary charge distribution. This is 4 pi E naught. And now we have a line integral because it is a line charge distribution. So R is Z minus Z prime. It's pointing along AZ axis. And DL prime is DZ prime. And the charge distribution is, of course, rho L naught. So rho L naught divided by R cube. In this case, this is Z minus Z prime cube. And Z prime goes from Z1 to Z2. So if I rearrange this, I can take RL naught outside. So this is rho L naught over 4 pi E naught. Integral of Z1 to Z2 of Z minus Z prime over Z minus Z prime cube times DZ prime, and it's pointing along the Z axis. Of course, Z minus Z prime cancels this, this becomes a square, and if I substitute or so let this Z minus Z prime is U. So let Z minus Z prime is U. So therefore, minus DZ prime is du, because z is assumed to be constant with respect to z prime. And z minus z1 is u1, z minus z2 is u2. These are the boundaries. So if I plug all these expressions into here, so E will be rho L naught over 4 pi E naught, integral from U1 to U2. Now it's 1 over z minus z prime square, so 1 over u square, and dz prime is minus du. So this is du, and I'll put a minus sign here. So the integral of this one is E is minus R L naught over 4 pi E naught. And this is minus 1 over U from U1 to U2. This is from U1 to U2. So this minus of minus will be plus. So the electric field vector will be rho L naught over 4 pi E naught. 1 over U2. U2 is 1 over Z minus Z1. Sorry, Z minus Z2 minus 1 over U1, which is 1 over Z minus Z1. And the unit vector is along the Z axis, So this is the electric field vector along the Z axis due to this finite line charge distribution. So the electric field along the Z axis due to this finite charge distribution is given by this expression. And if we were asked to determine on a different point other than the Z axis, if we have rho, then what we'll do is we'll update the R vector and the R prime vector, and then we'll have a new R. So we'll substitute that R here and solve the problem. So substitute this R and solve for the problem. For instance, let me just say, I'll just give you, so for instance, if you are asked to determine the electric field at this point outside the Z axis, what we need to do is we have to determine Z and R and R prime. Now in this case, R is here. Let's say R is the vector from the origin, from 0, 0, 0 point to the field point. So in this case, R has two components. One is the arrow component, and the other one is the Z component. So this is rho times arrow plus Z along the Z axis. It has two components. One is arrow and the other one is Z. And R prime is, if you see, R prime is the distance from the vector between the origin and the Z prime. So this is R and this is R prime. So R prime is Z prime along the Z axis. So therefore, R minus R prime is our vector between the source and the field point. So in this case, it will be rho times arrow plus Z minus Z prime along the Z axis. So we have R. So the vector R is given by this. And if you want to determine the magnitude of R, so the magnitude of R will be the square root of rho square plus Z minus Z prime square. So we have the magnitude of R. We have the vector R. So what we need is just simply plug in the value. So the denominator is basically the magnitude, not bold. So this is the magnitude cube. So you have R vector, you know the magnitude, you know rho L, that is rho L naught, you know dl prime, this is the differential length along the z-axis, which is dz prime, and the lower and the upper boundaries are the same. So z prime, it starts from z1 till z2. So you substitute these values and then the rest is math. So you can integrate and determine the electric field. So always for arbitrary charge distribution, you have to specify the source point where you have the charge distribution, and you have to also define the field point where you want to determine the electric field. So after you specify those points, first determine the R vector, that the vector between the origin and the field point, and then determine R prime, which is the vector between, again, the origin and the source point. Take the difference of the two to determine the vector R, and then determine also its magnitude, and then substitute the expression to determine the electric field. So the denominator is always a magnitude. What you see here is a magnitude. So, and then we can solve the electric field vector, or we can solve for E. And this is true if we have arbitrary charge distribution where Gauss law cannot be applied.